The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So, thanks for coming today. This is a key lecture in the Fourier, in the application of Fourier, you could say. So convolution is the big word. And a major application of convolution is filtering, signal processing. So we'll develop that application, but it's nothing but convolution. So the key idea is these convolution rules, where they come from, and what these new symbols, that's the symbol for the convolution of two functions. They could be functions here. Here they're long vectors of coefficients. And so these are the rules. So it's just a little bit of algebra, but it just is so central to all this subject. Signal processing is certainly the most important little thing to know. That if I multiply two functions, so that's where we started last time. If I have a function f with Fourier coefficient c and a function g with coefficients d, then, oh, wrong. I convolve the coefficients, right? So f has coefficient c, g has coefficients d. So if I multiply the functions, I definitely do not just multiply each c times the d. I do this convolution operation, which we have to remember. That's our main first step, is to remember what that was about. And then this is the other direction. So we didn't see this before. I mean, this is always this fantastic symmetry between physical space and frequency space. And convolution in one is multiplication in the other. It's so easy to remember. If I multiply in one space, I do a convolution in the other space. If I do a convolution of functions, I do a multiplication of coefficients. Yeah, so that's the rule to know. And now if we expand on it by sort of seeing again what it means. So let me do a quick repeat of this first step to remember what this symbol, convolution symbol, means. And then another thing I have to do, here I'm talking about the infinite case, functions, and with a whole infinite sequence of coefficients. I've got to do the cyclic case too, which goes with the discrete transform. Okay, but let's start with the infinite case as we did last time. Let me, here's something, here's a suggestion. We had f of x. We started with f of x as the sum, and remember, to have nice formulas, we're doing the complex version, ck e to the I kx. Let me suggest something. Let me write z for e to the I kx. So I'm going to just write that as the sum of ck z to the k. So z is e to the I x. It's just not, I mean, this is like a good point to make anyway. When we have this e to the I kx, it's natural to think of that as a complex number on the unit circle. Right? That's always the message. E to the I real is on the unit circle, absolute value 1. And this is great for periodic functions, because if these functions have period 2 pi, and if we think of our function as being on the circle, it obviously has period 2 pi. I mean, just the picture says, yes, if I go 2 pi, I come back. So x is the angle here, right? That's x is the, in this picture, a little bit unusual maybe, x there would be the angle. And it's just a little bit easier to write. And maybe it even has an official name, the Z transform. How do you like that? You learn a transform just in 14 seconds, right? Okay, it's a Z transform. All right, now it'll make it easier to multiply by G. So G is going to be the sum of dk Z to the k. So just think of these as long, well, I'm tempted to say long polynomials. I mean very long, because they can be infinite series, infinite negative powers and positive powers. But just think of it as a bunch of powers of Z times a bunch of powers of Z. And if you multiply a couple of polynomials, you're doing convolution. I mean, I guess my message is you've been doing convolution since the 2nd grade. That's the real message. Here, let me show you. This is convolution 2. Suppose I have to multiply 123 times 456. Okay, so what do? Remember back, right? It's a long way back, but we can do this. 1, 2, 3 times 4, 5, 6. So I multiply the 3. Oh, there's a little point where that 2nd grade teacher is going to panic. I'm going to write that as 18. And that's 15, and that's 12. Sorry about that. Yeah. Okay. And 12, 10, and 8, right? 4, 5, and 6. So you see the 9 multiplications that you have to do? 9 multiplications, 3 times 3. Okay, right now, these, imagine those they could have been longer, but they were finite length filters, we could say. So, okay, and now what does convolution do? Just what you did when multiplication. When I add 12, 10, and 6, what am I doing? I'm putting together the 3 times the 4, the 2 times the 5, and the 1 times the 6. That's what convolution, those are the things that convolution puts together. So we get an 18, a 27, 28, 13, and 4. So I guess I'm saying that, all right, here's what I really want to say. I want to say that the convolution of those with these, 4, 5, 6, is this sequence here yeah, that's right, 4, 13, 28, 27, and 18. If you just look at that, where did that 13 come from? Let's just remember, where did that 13 come from? That came from, this was Z to the 0. This is the Z, this 13 is 13 Z to the 1st power, right? We're just checking all the powers here. There's 13 Z to the 1st power. Where do we get a 1st power? We get a Z to the 0 times 5 Z to the 1. So that's 5 Z to the 1. And we also have 2 Z to the 1st power times 4 Z to the 0th power, right? The 2 times 4 gave the 8. So the 8 from there and the 5 from there produced that 13. And that's just what you did in multiplication, right? It's just, so that's a multiplication of 2 series that's not cyclic. This is definitely not yet cyclic, but we'll make it cyclic in a minute. This is the infinite one, except that we had all zeros beyond. Okay, so that if you, in non-cyclic convolution like this, if I have length m and length n, then I get length m plus n, maybe m plus n minus 1. Okay, so that's convolution. Without carrying numbers, yeah, without doing it right. Okay. So, and what does that correspond to? Let me just, so you see it every way. That corresponds to 1 plus 2z plus 3z squared multiplying 4 plus 5z plus 6z squared. and it gave, that's times, and it gave, you know, this thing up to 18z to the fourth. Just exactly the multiplication that you've always done. Okay, so that's the idea. Over on that board, I'm going to put a formula for this convolution operation, but this, my point on this board is you've done it always. When you multiply a couple of polynomials, you collect powers. And that's all convolution is doing, collecting each power separately. Okay, let's do it. So then f of x, g of x is, when I multiply that polynomial or series by that polynomial, I get some polynomial in with coefficients. Oh, I was changed to L just to have a different symbol there. And what was the formula for L? For HL. What is the coefficient of z to the L? Well, if I multiply that by that, do you remember the story there? When I multiplied that by that, and I looked for the terms that gave me z to the L. Okay, well, that means that this power times this power is going to be z to the L. So that the index, do you remember what happened? It was a lot of different, just the way, this is HL is, here's H2 or something. I've got to do an addition because a bunch of C's come in with different D's. So, and what's the deal then? CK comes in with which D? This is the magic number there. What's the subscript that if I look at the coefficient of z to the L, I look at each of these, and then I pick out the one of these that will give me a z to the L. And which one is it? D sub L minus k. It's that magic quantity that the eye spots perfectly. K and L minus k adding to L, simply because z to the k, z to the L minus k multiplies to z to the L. Same thing, right? Okay, so this is, now I'll use that notation. This is C convolved with D. C convolved with D is H. C convolved with D is H. So this is the else component. C convolved with D is my symbol. This H is the convolution then. That's the convolution rule. It's just whatever operation you have to do to get the right answer. The right answer when you multiply. Yep. Okay. So that's this one now. Ready for the discrete case? The finite case? The case when you have power, when z becomes w. The discrete case, the cyclic case, sorry, maybe emphasize the cyclic case, meaning it circles around, is the case when z becomes this very special z on the unit circle that we know as w. Okay, and we have to say, and of course it's wn. We have to tell you in the cyclic case how long the cycle is. So this would be a case, watch what you do here to make this cyclic. Okay, I have 3 inputs, so n is 3 here. Now I'm going to do the cyclic one. So instead of z's, I should be putting w's. I will. I'll put, just to emphasize, it's just good to think of it with the w there, because the w has this special property that's critical to everything. Okay, so now I think of this as 1w to the 0, 2w to the 1, and 3w squared. I'm thinking of this same multiplication here, but now w's. Okay, so I'll end up with 18w to the 4th, and 4 was the constant, and 13 w's, and so on. All these numbers. what's the difference? Ready for the key point now. What's happened in this cyclic case? Well, the difference is, what is w to the fourth? If we're in the cyclic case, n is 3 now. Our guys have length 3. Our circle is w now is 1/3 of the way around. So that's my w. Here's my w squared. Here is my 1. But here it is also w cubed. So w is the same as w to the fourth. W squared is the same as w to the fifth. So what's the difference? What can I do now? If I'm in this discrete case, then my inputs are a vector of length n, 3. A vector of length n, 3, and I want to get out a vector of length 3. I'm not happy with that in the cyclic case, because I'm not happy with w to the fourth. So now tell me again that when I do the multiplication, and I just do it, there's no difference except in how I write the answer. 18w to the fourth is the same as w. W to the fourth is the same as w when n is 3. So that 18w to the fourth cycles back in with this 13. So now if I do can I show you the symbol? I'll just do a little circle there to say this is now the cyclic convolution. Then this isn't the answer anymore. The answer now for cyclic convolution, I only want 3 numbers. And if you can tell me what those 3 numbers are, we've got it. Let me move those over a little to make room for the 3 numbers. So there's the answer, the space for the answer. What do I write in? What's the constant term? 31. What's the constant term? It's 31. Right, it's 31. Where did 31 come from? It came from, you could say, cycling that 27w cubed back with the 4. Because there's no w cubed is the same as 1. So I've gone around the circle when I come around to w cubed, so that 27 and 4 combine into that 31. And let's see, how else so what multiplications am I doing here? 1 times 4 gives me the constant. 2 times 6, that's 2 w's and 6 w squareds, that's 12w cubed, that's 12. And then 3 w squareds and 5 w's is 15 w to the cubed, but that's the same as 15. So that's why we get 31. We've got 4, we've got 12, and we've got 15. Okay, now what's the second component, the w component of the cyclic convolution? Tell me what number do I write in that middle position? How many w's do I have? 31 again. This 18 is coming back by 3 to 13. You see, I could have done that multiplication. So it's coming back to 31. Am I going to get another 31? No. What's the w squared guy? 28. Yeah, 28, because there's no w to the fifth to come back, and 28 has already. So 28 used its 3 multiplications. The 31 there used the 4 and these 2. This came back over to here. And this 31 used this 18, came back. I could have put the 18 here. You know, I could have lined it up just 3. So I'll write a formula for it. So that's the answer. 31, 31, 28. Could I just suggest a little check on that, just to check on the numbers? I think that if I add up these numbers, I get 6. And if I add up those numbers, I get 15. And if I multiply that, I get 90. And if I add those numbers, I get 90, right? So those add to 90. So I'm just saying a numerical check is add these, multiply by the sum of those, and you get the sum of those. Why is that? It somehow seems right, doesn't it? Because somehow I've taken all 9 products here, and so when I add all the results, I'll have the sum of all 9 of these possible products, so I'll have 6 times 15. Actually, here's a good way to look at it. In doing this, I just set W equal to 1. I just set W equal 1 in the polynomials. When I set W to the 1, this becomes 6, this becomes 15, and the answer becomes 90 when W is 1. Yeah, so that's another way to see. And actually, this multiplication, the second grade version, had W, well, I'm almost going to say W equal 10, but it's not quite that because it's written in the opposite order, right? If W was 10, this would be 1. Well, anyway, W can't be 10. It's got to stay on the unit circle. So, yeah. So somewhere in the non-cyclic case is something like W equal 10 or W equal 1/10, maybe. Whatever. Okay. Could you take the convolution now? Let me give you just another example and do it mentally. What's the convolution of 0, 1, 0, 0? Let me make it a little longer. Shall I take first of all, the non-cyclic convolution of 0, 0, 1, 0? Okay. What's the ordinary, how long is the answer now? This is like just practice. How many components am I going to have in the ordinary convolution of those two guys of length 4? I think it's 7. I think it'll be 7, because we'll have here 1, we have z to the 0, z to the 1, z squared, and z cubed. And here we'll have, again, the same. It'll go up to z to the 6, but remember there's a z to the 0, so that's why we have 7. And what will it be? What will it be? I guess, actually, this wasn't a brilliant example, was it? But let's finish it. So I'm just multiplying z by z squared. So what do you get for an answer? I think the 1 shows up in the z cubed. Is that right? Yeah. Yeah. Z to the first power here, z to the squared here, z cubed here, and we always have to remember everything in chapter 4 starts at 0. The 0, z to the 0 is the first one. Okay, that's not too great an example, because if I do, what happens if I do the circular cyclic convolution? What would be the cyclic convolution? Now I'm expecting 4 guys only, right? Because cyclic keeps the same length. And what would be the answer? Well, there's nobody to fold back, so it would be just 0, 0, 0, 1. So let me update this a little bit with a 1 here. Okay? Just to practice. So suppose I do that convolution. Uncyclic first. What do I change here now? I've now got a z squared and I've also got a z cubed, but I only have a single 1 there. Oh, let's make it a little more interesting. Okay, make it like so. All right, z plus z squared is what we're looking at. Z plus z squared is multiplying z squared plus z cubed. And in the long form, what do I get? Let me make space. Tell me what numbers to put in. If I multiply z plus z squared times z squared plus z cubed, I get what? 1z cubed. How many z to the 4ths? 2 of them. How many z to the 5ths? 1, and nobody there. Okay. And now the cyclic version would be what? What's my answer now for the cyclic version? Let me take those out. So the cyclic version would bring the 2 back to the 0, would bring that 1 back to there. That 0 will still be 0. And I check that I've got that I haven't missed anything by adding those up to get 4 and adding this up to get 2 times 2. Yeah. Okay. So that's the rule, and it's a lot cleaner to see these answers than to see this formula. And I need, actually, of course, now mentioning that formula, I need a cyclic formula. So can I write above it the cyclic formula? What do I get when I'm instead of this sum, which went from k equal minus infinity to infinity, in the cyclic case, hk is just going to be a sum from 0 to n minus 1, and there'll be a ck and a d something, and now this is the cyclic case. So I guess, yeah, well, this makes us, I think what our situation now is we understand the cyclic case from examples, and now we just have the job of how do I put it into algebra? How do I put it into symbols? What's the point? CK, D, N, let's say. But what? Oh no, I'm looking for HL. Yeah. So what's the deal? Here, L was K plus that one is the sum of that one and that one. So here, L is the sum of K and N, but what's the but? I mean, somehow I've got some wraparound to do, right? When I'm doing the cyclic multiplication, and I'm doing that wraparound because because W to the nth, I now, the wraparound comes from that, right? That's why I never get as high as n, because when I get to n, I go back to the 0th power. Okay, so what's the relation of k and n and L here? Yeah, we just need the right word to express it. So k, what's the word? Mod. Yes. So that's the word I'm looking for. K plus n is L with wraparound. And wraparound means the nice notation that people use is mod n. Let's practice. What is 2 plus 2 mod 7? 4. 2 plus 2 is 4, even in 18085. Right. Okay. But 2 plus 2 mod 3 is 2 plus 2 mod 3 is 1. Everybody sees it? I'm taking z squared times z squared, z to the 4th. But I'm doing with n equals 3, so z cubed is 1, so that z to the 4th is really just z to the 1st power. Yeah. So this is the little nifty notation that says make it cyclic. Bring it back so that there are L only has the values here 0 up to n minus 1, and then stops. Okay, so we'll have more practice with examples when we do some filtering. Have you got that fundamental, so we've talked about this rule 1 here. F times G goes to those coefficients. And if it's the cyclic case, then I put a circle around that star and I do the wraparound. Yeah. But it's just what, it's the Z transform, it's polynomials in Z or polynomials in W. And when it's polynomials in W, you use that special property that W to the n is 1. Yeah, okay. Okay, now I see I've written another line there that I could convolve functions. Oh, let me do a couple more examples. Couple of examples first before I go to that line, okay? Suppose, yeah, so I'm up to this line. Oh, yeah, a couple of examples here. Let's see, what example would I want to do? Let's see, there's a very, okay, I want to do one example with a delta function somehow. One example with a delta function. Yeah, one example with a delta vector. Yeah, let me take the function g of x identically 1. Okay, constant function in this rule. I want to see what happens with the rule. Okay, then f of x, g of x is the same as f of x, right? Because this function g of x is so simple, it's just 1. Now, what about the coefficients? So I have the coefficients of C. What are the Fourier coefficients? What are the D's? Ah, yeah. What are the D's? So I'm testing my rule on a really, really simple case, g of x identically 1. What you have to tell me, in order to check the right side of the rule, you have to tell me the Fourier coefficients for that very special function. What would be the Fourier coefficients? If I expand the function 1 in a Fourier series, what do I see? I see a 1. Yeah, that's it. I see 1. So what are its coefficients? D0, right, is 1, and the other D's are all 0, right? So my vector of D, my vector of D's is a whole lot of zeros on the negative side, a 1 right there in the center, and then a whole lot of zeros. And now I want to convolve that with C. Do you see what I'm practicing the convolution rule on a case that's so simple it's confusing, right? Yeah. So I mean it's a big mess, this multiplication. But if D, yeah, so what am I going to get? Yeah, tell me what do I get out of this? If D is this vector, is this, if D has this property that D0 is 1 and others are 0, all others are 0, so this is my little example, what does this sum boil down to? Well, I only get something when L equals K, right? I only get something when L equals K, because then I have D0, and that's the only D that's around. So in this sum, something happens only when K and L are the same. And then what happens? Then I have a 1, I have CL, and that's HL. So that's all I'm concluding then, that this H is the same as C. I'm sorry, it's so dumb. My point is that in convolution, this is the thing that acts like 1. Because in multiplication, that's the thing. That's the function that acts like 1. In fact, that's the function that is 1. So this is the 1 in, would you allow me to do this? I'm going to create a matrix with these D's. Yeah, there's another way to see convolution. Yeah, there's another way to see convolution and discrete convolution. Maybe the discrete one's the better. Yeah, can you stand one more way to write the formula? One more way to write. Now I'm going to do discrete convolution. Discrete, cyclic. So how am I going to write it? I'm going to write it by a matrix multiplication. Because you know that in this course, a matrix is going to show up. So it's going to be a matrix multiplication. So I just have to tell you so this is going to be some matrix. Let me take n to be 4. So then I have this, you watch. So I have 4 D's, and the output is the 4 H's, and the rule I'm following is this rule, is this the same old rule, but with the cyclic part, and now I want to show you the matrix that'll just do this. Look, I put the C's in the first column, and then I go, here's another, so it's a cyclic matrix. So let me make it, let me finish it up. It's going to be 4 by 4, it's going to be cyclic, so I have a C0, 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 C0 on the diagonal. That's fine. That's because z to the 0 is multiplying all the d's and leaving them in place. And then I have C1s, and then I think I come around again here for a C1, and I have C2s. Let's see, where's C3, C2, and I come around again to a C2 and a C2, and C3 comes around to a C3, a C3, and a C3. Well, I hope you can see this. This is a cyclic matrix. It's only got one. It starts with a vector C, and those are on the diagonal, and the diagonals wrap around. That's the other word that you often see when you see the word cyclic. Wraparound. It's because you think of a circle. You know, if you go the second time around, it's wrapped around the first time. Okay, just can you look and see that this is the right formula for H naught? H naught is C naught D naught. Where does that come from? Remember, H naught is the coefficient of z to the 0 power in the answer. So it comes from C0 D0 to the 0th power in the input. And then why is there a C3 D1? Why is there a C3 D1 and then a C2 D2 and then a C1 D3 all piling up into H0? Tell me now, why is there a C3 D1? Because we're doing mod 4 is one way to say it. 3 and 1 add to 4. Because C3 is the Z cubed guy, a W cubed guy, and D1 is the coefficient of W to the 1, and W cubed times W to the 1 piles back into the constant. And you see the pattern of that matrix? These matrices are very important. So they circle around. We've actually met a matrix of this type the first day of 18085. It was, what was that matrix? It was one of our 4 great matrices. And now here it is back again. Which one was it? Well, you remember the letter for it, which isn't going to change. And do you remember the particular matrix? Well, everybody does remember that matrix, right? 2's were on the diagonal, -1's were on the diagonal, and the diagonal continued. -1 was on this diagonal, and that continued, and 0's was on this diagonal. So this is cyclic convolution, the circulant matrix, cyclic convolution by C. What's the C for this that produces that convolution matrix? It's got, well, there it is. The first column is it. Right, right. And somehow that's I would say that that's an even vector. I mean, why, it's sort of, I associate it with cosines. It's an even vector. Here's the 0 term, and then these are the same. Yeah, not to worry about that part. Do you see that we've seen that matrix before? And the cyclic convolution means you take, it's second differences, of course. We're taking second differences, but everything in our world is cyclic. So the result, the Z4 is the X4 is X0. So we're taking second differences. Well, maybe I should say D. We're taking second differences D, I, 2 di's minus D, I minus 1 minus D, I plus 1. I don't know if this is. So there's a -1, 2, -1, and we're cycling around so that D0 is D4, and D1 is D5, and D -1 is D3, whatever. Yeah. Okay. I just reminding you, we've seen these before. Okay, so this is another way to remember the formula. Okay, now can I ask a practical question? A practical question. Let me bring back this second grade multiplication. Well, I have a granddaughter named Elizabeth, I'll have to admit. I didn't think about mentioning Elizabeth. She's 6. And she delights in sending me long multiplications. I mean, really long. And then every time I talk to her on the phone, she says, "Have you done that one yet?" And I say, "I'm working on it. I've got MATLAB at work," because they're ridiculous, and I haven't figured out how to tell her. I mean, she just writes page after page times 100 plus 3 minus 7, just as whatever she thinks of. Okay, now I need help from the convolution rule here, actually. So let's suppose that Elizabeth has given me a multiplication in which I have 1,000 digits times 1,000, right? Which Mathematica is prepared to do exactly, right? MATLAB will mess up, but Mathematica and Maple and symbolic packages will do exact computation. So what would be the right way? Well, let me make it 1,024. 1,024 digits times 1,024 digits. Let's do the cyclic version first. Elizabeth doesn't know about cyclic. Maybe I could teach her that. That'll keep her busy while I'm doing the multiplication. Okay, right. Okay. Only her older brother would explain it to her. That's the trouble. Okay, yes. Okay, so how am I going to do, or how are you going to do on the quiz, multiplication of 1,024 digits times 1,024? And I'll make it easy by making it cyclic. So I just want 1,024 digits in the answer. Okay. How would you do it? Well, before today, you would have just multiplied, right? You would have written down 1,024, 2 lines of 1,024 done in addition, and you would have had 1,000,000 multiplications to do. But how would you do it now? Oh, apart from giving it to Mathematica. What's a faster way to do it? What's a faster way to do a convolution? The fast way to do a convolution is to use the convolution rule, go this way, to take these numbers, these 1,024 numbers in C and these 1,024 numbers in D, and what do I have to do? I want to use the convolution rule because multiplying is fast. Yeah, now I've got functions here. I really, but I'm in the cyclic case. So I'm in the cyclic case. So what should I? How can I change this to be the cyclic case? This is like F, J, G, G, J. So multiplication of components of things in function space is convolution of coefficients. So now this is the cyclic. So let me make it cyclic. Okay, right. Okay, so again, what's your problem? The problem is to do this cyclic multiplication. What's the idea? The idea is to transform C back to F, to transform D back to G, do the multiplications. Now I have only 1,024 multiplications, not 1,024 squared. That's the point. And if I do this directly, I've got 1,024 squared multiplications to do. Much better. Transform back to here, do just 1,024. What's the MATLAB command for that when you're multiplying each component by itself? It's not the dot product, notice. It's not the dot product because I'm not summing here. Do you know the MATLAB command? If I have a sequence of numbers, a vector f of length 1,024, and I want to get that result. What's the result? It's a vector of length 1,024 that takes each f times its g, but doesn't do any add. That's what's there. What's the MATLAB command for that? Dot. Yeah, dot star. Right. So that dot says component by component. Okay, so what's the plan here? I do C's back to F by the Fourier matrix, D back to G by the Fourier matrix. Then I do a very quick multiplication, and then what? Then I mustn't forget that I'm in frequency space. And what do I have to do? I've got to get back into coefficient space. So I do the inverse transform of, so I'm doing, here's the formula then. I'm doing the inverse transform of F, so of the transform of C dot star the transform of D to get C, D. Is that right? So I took C and I got back into the function. I took D and got back to its function with the Fourier matrix. Okay, I'm in the Fourier, and now I'm in this space. I've added up coefficients to get in this space. Now I do the dot star, the fast one, and then I transform back. So why is that faster than just doing it? Because what's the cost of F times C? And how am I going to do that? I'm going to do it with the fast Fourier transform, right? That's the point. I can multiply by F or by F inverse faster. So I have three of these transforms. I've got to get two guys into the other space and the answer back out. So I have sort of three of these n log n's. But that will easily beat n squared. right? So that's, so if you have a convolution to do, and it's possible to do this, get into the other space where it's just an element by element multiplication. And that would apply in either direction because the rule goes both ways. If I have this convolution to do, I would find the coefficients here, the C's, the coefficients of D, of the G's. I would do this one by one multiplication, and then I've got then I have the Fourier coefficients of the convolution. Right, right. Okay. Do I have a moment? Well, hardly. Just can I write down what the formula for a convolution of two functions would look like? Sorry, f of x convolved with g of x. Let me make it cyclic, just to see what it would look like. What am I expecting for that convolution? I'm expecting a function, and somehow there's going to be an integral, because instead of a sum, where I had sums, but now I have integrals. And here's the point. I'll have f of t times g of x minus t dt. It's all I'm asking you to look at is the fact that the way here I had k and L minus k. For functions, your eye sees that right away as a t and an x minus t dt. These add to the answer. These add to the result at x.
Is that the cyclical or just
That would be the cyclical one, yeah. So I could go 0 to, these are all periodic functions, so all 2 pi periods are the same. The book will do that properly. Okay, we've got the filtering to discuss on Monday. You can see that this convolution stuff is just takes a little new thinking, but it comes out nicely.